Welcome to Spring LIB.
This problem is problem 8. However, the only difference being that instead of mentioning the electric flux, they have just electric field. So we can start by writing the electric field. And before that, let's give an introduction to the problem. This problem, we have a circular region of radius capital R. R is equal to 3 centimeter that carries electric field which is varying. Electric field, the varying electric field in this case is goes by 0.5 volt per meter. Volt per meter second. Small r is the radial distance, capital R is the overall full radius of this, and t is the time. Now phi of E is always given as E dot ds, where ds in this case is the area element, of this one over this entire surface. So over the entire cylindrical surface in this case. So we need to find out the magnetic induced field for case where we have r is equal to 2 centimeters. So if r is equal to 2 centimeters, it is less than the capital R. In the Ampere's law, integral P dot dl not I, which is enclosed, plus mu naught I d is the displacement current. Now for our case, the closed current going through the circular region. So the only current that we need to worry about is this, that is called the displacement current ID. This one is the ID. To calculate the displacement, now in this case, we need to first evaluate this term. We can see that if I take a derivative of this, of phi of E, t will just go away. So I just need to integrate this with respect to ds. So we can start doing that. And this, let's also evaluate this first. So this should be equal to b into simply pi r. Pi r is the overall length of the loop, and b is a magnetic field which we consider constant along the loop. So if we try to evaluate phi of E here, that is equal to E dot ds, and the only element r, which is so E, area element in this case is 2 pi r dr. That gives us t comes out as usual 0.5. 2 pi also comes out of the integral. We integrate 1 minus r over r dr. So integrating this, we have t pi. We'll take the first part. The first part is r dr. Integral of r dr is r square over 2. And integral of this part is minus r squared dr over r, which will be equal to minus r cube over 3 with an r. Limits for integration were 0 to some r. When we put 0, 0 goes away, so we'll just have this as the final integral. And this is a page. So we'll again write down p 2 pi r is equal to mu naught epsilon naught mu naught pi, and remember that we have to take derivative of this. T goes away in that derivative, we just have pi r square over 2, and all the other terms which are r square over 2 minus r cube over 3. And for r equal to 0.02 meters, with capital R equal to 3 centimeters, that is 0.03 meters, we get a value of P which is equal to, this is the magnitude of P, that's 3.09 into 10 power minus 20 teslas. Next we do the same calculation for the other part, which is R is equal to 5 centimeters here. Now this case is when R is greater than capital R. Capital R. And the only difference which we will have is this. Now this integral had an upper limit of small r radial distance. However, once we go to a distance which is outside the entire cylindrical surface over which the electric field actually exists, this electric field flux exists only within this region. It doesn't exist outside this region. So the maximum value of r that we can go is just capital R. If I take capital R, then so the phi of E all the way up to capital R is equal to T by R square over 2 minus R cube over 3R. So this is R square over 2, that is capital R square over 2 minus R cube over 3R. So as you can see, this now becomes T by R square over 6. So our magnetic field is now 2 pi R. This R is outside, so it is 5. 1 over 6 mu naught epsilon naught pi R square. The T goes away because we have to take a derivative of this with time. The magnetic field now evaluates in this to 1.67 in 10 power minus 20 Tesla.